In video 78 of Tensor Calculus, we'll introduce the concept of Gaussian curvature, which is a property that quantifies the curvature of a two-dimensional surface. What you see here is a surface known as an elliptic paraboloid. If you look at it from the top, you see the cross-section of an ellipse. If you look at the cross-section from the front or the side, you see parabolas. Okay, well what we want to do today is to use this surface to illustrate Gaussian curvature. Now, Gaussian curvature is something that was developed by Carl Friedrich Gauss in the early 19th century. Okay, we'll start by putting a point on the surface right here. And through that point, we will construct a tangent plane. Tangent plane is something you should be quite familiar with at this point. This is the plane that touches our surface at only one point right there. All right, to kind of orient ourselves a little bit, I'll put up the basis vectors that we've talked about many times. Here we've got S1 and S2, which are the surface covariant basis vectors. They lie in the tangent plane. And then there's the normal vector n hat, which is a unit vector that's perpendicular to the plane. Okay, all stuff that we've done before. Well, let me then construct a normal, which is the line that is perpendicular to the plane, pointing in the direction of our normal vector, basis vector. And to make things easier to see, let me clean it up a little bit. I'll take the basis vectors off, and I'll also remove the coordinate axes here. Things are going to get pretty cluttered here in just a minute, so let me take these axes off altogether. All right, next thing is this. We will construct a line through this point that lies in the tangent plane, and it's this line right here. For now, it's just going to be in an arbitrary direction, but it does lie in the tangent plane, and therefore it's perpendicular to the normal itself. So, since these lines intersect, we can use them to define another plane. Let me take the tangent plane off, and I will define a plane through these two lines that we've constructed. So you can see where the plane is here. And that plane, of course, then slices right through our surface with this intersection that's this arc. Let me draw that as a line. So this curved red line is now the intersection between the plane we've constructed and our surface. Now, if I turn it like this, then you can view these objects as objects that lie in a plane. The two straight lines are in the plane, and so is this intersection. So we can treat this line, this curve, as a two-dimensional function in a two-dimensional space. We could call the red line here the horizontal axis, measuring a coordinate u, and the blue line our vertical axis, measuring a coordinate w. And we've constructed it in such a way that the curve we've created here is then going to be a function of u in this two-dimensional space, and if you notice, it is tangent to the horizontal axis at the point of interest right here. Well, if you go back a video, we derived a formula for the curvature of such a curve in two-dimensional space, and in the process we said that if our curve happens to be tangent to the horizontal axis, then the curvature of this function right here is simply going to be the second derivative of the function with respect to the horizontal axis. In other words, the curvature of this arc that we've created can be represented this way. We're treating w as the length here, u as the length here, and therefore our curve is a function w, a function of u, and if we take the second partial derivative of it with respect to u, then we're going to get the curvature. So right now, at this point, the curvature of this intersected line here is negative 0.042. Okay, let me take the plane off. We'll go back in this direction. And we said when we started that this is an arbitrary direction. But now let me begin to rotate this line. I'm going to change the direction of the line by rotating it to the right. And notice as I do, watch the numerical value here. As I rotate, this value gets more negative. So as I go back to the left again, the numerical value is getting less negative as I go back. So it's getting closer to zero, less negative, and so on. And now it begins to go more negative. All right, so that means that there's a point in here where we reached a maximum. Let's look at this spot right about, where would it be? Right here. So at this point, the curvature is negative 0.048. If I go a little bit to one side, over here, notice it goes more negative. If I go back again and go to the other side, it gets more negative as I move in this direction. So what we're saying is that right here is the maximum value of curvature. We've located the direction of this intersection that creates the maximum curvature of the intersected curve. All right, well, let's repeat the process. This time we'll create another line, a green one, and we will call this the v-axis. We're going to measure a coordinate value v in this direction. We'll go through the same exercise. We'll create a plane through these two lines and an intersection. So this green arc is now the intersection of this plane with our surface. I'll take the plane off. And everything we said about the red arc is true here, so we can find the curvature of this green arc by taking the second derivative of our function with respect to v. So this value is the curvature of our green arc down here. And as before, if I change the direction of the green line, I change the value of the curvature. All right. But what I've really done is I've created a three-dimensional coordinate system. I've got the dimension of u out here, and v in this direction, and w over here. So I can treat the points on the surface as a function of u and v in this three-dimensional coordinate system. So we'll have a multivariable function w that's a function of both u and v, and that will identify every point on our surface from the perspective of this new coordinate system. Well, what that means is I can take another type of derivative too, which is this one. I can take the second partial of w with respect to u and then of v. And as you might imagine, as I change my direction here, that value changes as well. Okay. Well, let's see what happens to the numerical value of the green, the v dimension here. As I begin to go in this direction, rotating to the left, notice that the value here gets more negative. It's going lower, and then it's getting less negative. I go back again over here, and it gets lower, and then it starts going less negative again. So what that's telling us is that right about here, this spot right there, we find a minimum value of our curvature. So if I go a little to the right of this, this is going to become less negative. Go to the left or right, it'll go less negative. Up here, if I go a little to the right or left with the red arc, it'll become more negative. So what we're saying is that this value right here represents the greatest possible curvature in this exercise, while this one represents the minimum curvature. Now what Gauss discovered is that you can always perform this process on any surface. You can always find a maximum curvature and a minimum curvature at any point on any surface of any manifold. And he defined these two values as the principal curvatures of the surface. So let me just put those up right here. we usually denote these with the Greek letter kappa 1 and kappa 2. So kappa 1 in this spot on the surface is this value, kappa 2 is this one, and these are the maximum and minimum curvatures respectively. Now he noticed a couple of other things too, and he was able to prove it. Two other things happen. One is, if you look at it, the two lines that we've constructed now lie perpendicular to each other. So the v-axis and the u-axis are at right angles to each other, and that's not an accident. That will always happen. When you find this maximum point of curvature, the maximum and minimum, the two principal curvatures, you'll find that the axes you constructed will be at right angles. The other thing he noticed, and he again was able to prove it, is that this second partial derivative with respect to u then v vanishes. At the point where you've located the principal curvatures, this second derivative, this mixed derivative, will always go to 0. So another way to perform this process would be this: to construct these two intersecting lines at right angles to each other, lock them together, and then rotate them together as a unit until that mixed derivative vanishes. So we'd move back and forth here to the left and to the right, and we'd rotate this until we found that spot right here where this mixed derivative vanishes to 0, and that's when we know we'd have the principal curvatures as the curvatures of these two axes. All right, well, it's possible to determine mathematically with analytic formulas exactly what angle is required to make this derivative go to 0. And so we don't have to physically go through this rotation. We can simply calculate that. So I'm going to put up another set of lines here that represent the optimum direction. So let me rotate these off a minute. The two intersecting lines that are represented in dashed lines are the direction required at this point to achieve the maximum and minimum curvatures. So what we're saying is we can simply rotate our axes until the solid line lies over the dashed line, and we know we've got the spot that we're looking for. And that can all be done mathematically, and we don't have to physically do this graphically. In other words, these values can be derived analytically without having to actually physically construct all of this. Okay, well, Gauss noted a couple of other things too. There are a couple of other invariants that show up in the process, and I'll display those. What he discovered is that if we look at the sum of the two partial derivatives here, or the second derivative with respect to u added to the second derivative with respect to v, and we got a particular value, what he noticed is that that was an invariant value. When we rotate these axes, notice that the sum of those two values doesn't change. The two curvatures are changing as we move the arc around a little bit, but the sum of these two values is always going to equal this number, no matter what direction it's pointing. That's quite interesting. He also noticed this particular invariant. If we take the product of these two derivatives, subtract the square of this one, and you could actually plug these into a calculator and see that if you multiplied this number by this one, subtracted the square of this, you'd get that value. And no matter where we rotate the axes, that value is not going to change either. It's an invariant where the rotation is concerned. All right, well, that led him then to define these quantities. This one he defined as the mean curvature of the surface. Now, he actually defined the mean curvature as the sum of these divided by 2, but in tensor calculus, we simply define the mean curvature as the sum of the two. And the mean curvature is an invariant value that is represented by this expression. And in this case, he defined this expression down here as Gaussian curvature. It's an invariant quantity, And all four of these quantities, the principal curvatures, the two of those, the mean curvature, and the Gaussian curvature, are invariant quantities. They are quantities that are properties of the surface itself at this point. Now, let's rotate this back to the optimum spot here, which would be right here. Now, since the mixed partial here vanishes, that means that this expression right here, this term vanishes to 0, and the value of these two factors are simply the principal curvatures. So we can actually define Gaussian curvature as the product of the two principal curvatures, where the mean curvature is the sum of the two principal curvatures. So we add these together, we get this. Multiply them together, we get this. Okay, so let me make one more comment here before we move on. We have chosen a normal external here, a normal that points outward like this. If we had started with a normal inward, then we would find that these curvatures would be positive numbers because they're measured with respect to the positive direction of the normal. That would have led to the fact that the principal curvatures would have been positive as well. And when we add them together, the mean curvature would have been positive. So the curvatures, the principal curvatures, and mean curvature are all unique up to a sign. It could be positive or negative depending on which normal we've chosen to work with. However, when we multiply the two together, the two negatives multiplied together give us a positive value here. And if we were working with a normal that goes into the page, we'd have two positive values, and the product would again be positive. So what we're saying is that although these values might change to be positive or negative depending on the direction of the normal, the Gaussian curvature itself is not. It is not dependent on the direction of the normal. So the Gaussian curvature then becomes what we call an intrinsic property of the surface. The Gaussian curvature is a property of the space itself and has nothing to do with the normal. It is simply a property of this point, and we call it Gaussian curvature. Okay, well, let's do it again at a different point. Let's move our point of interest up here a little bit. We'll go up to a spot like this, and of course all these values have changed, and the two dashed lines now have a different direction. So if I'm going to go through the process here, I'd have to rotate these axes until the solid lines match the dashed lines, and that's somewhere right about here. So not exact, but we still have a little residual left over here. I'm not exactly on this line, but you get the idea that when this value goes to 0, then we will have located the principal curvatures, which are these. This is the mean curvature. This is the Gaussian curvature. All right, so let me do one other thing. Let's actually change the shape of our surface. And to do that, I'm going to move this parameter right here. I'll change it to, let's make it a 0. If I can set it right. All right, right here. Now what I've done is to create a simple paraboloid. If you look at the cross section, this is a parabola, but it's just a sheet now, a flat sheet that's bent over like this. Well, what I'm going to do now is to rotate the axes to match the lines up here. So I'll put the red line where it belongs. If I can get it there. All right, and notice what happens. The red line is now going straight across this surface, and there's no curvature at all. It's 0. And the green line has a negative curvature of negative 1,886. So it's curved in this direction, but not in this direction. So the curvatures are 0 and negative 0.1886. Well, that means that the mean curvatures is the sum of these, but it means the Gaussian curvature is 0. Now that might seem strange to you. How can something that's obviously curved be zero? Well, the Gaussian curvature is, as I say, a measure of the intrinsic curvature of the surface. And this is a case where this surface can be flattened out into a flat sheet without stretching or deforming it in any way. So its intrinsic curvature is in fact zero. It is intrinsically flat even though we see that it's curved. So you'd see the same kind of thing happen for a cylinder or a cone. Alright, let's try one more. This time what I'm going to do is to change the shape so that we have what's known as a hyperbolic paraboloid. This time we have parabolas this way and this way, but cross sections would give us hyperbola. Well, in this case, the curvature of the red line is in one direction and the curvature of the green line is in the other. So the red line is a positive curvature because it's curving upward around the point. Green line is negative. So our principal curvatures are K1 is positive, K2 is negative, and so the sum is some value that may be positive or negative, but the important thing here is that the Gaussian curvature is negative. And again, if we were to switch the direction of the normal, we'd find the sign of K1 to be negative, K2 would be positive, and this would be positive, but the Gaussian curvature would remain negative 0.0171. So the Gaussian curvature has nothing to do with the normal, and it's going to be negative whenever the curvatures move in the opposite direction like that. Okay, I think that's probably enough for this video. I think you've gotten an idea of how this works. Now, for the last 3 videos, we've talked a lot about curvature, and we've done it strictly on the basis of normal mathematical means. We haven't used tensor calculus at all in the last 3 videos. So as interesting as this is, I can almost hear you thinking, what does this have to do with tensor calculus? Well, we'll close that gap in the next video when we begin to talk a little more about the properties of our curvature tensor. And what we're going to find is that the curvature tensor gives us a means of deriving each of these values in a much easier way than the process we've gone through here. So that's what we're going to do in the next video.